Hello everyone! In this video we're going to cover the paper Composable Sparse Fine-Tuning for Cross-Lingual Transfer by researchers from the University of Cambridge, Quebec AI Institute, and McGill University. The main idea of the paper is composition using sparse fine-tuning instead of using modular adapter methods where a model is separately sparse fine-tuned for each language and each task. Fine-tuning on a task is done in one language, we call it the source language, and the resulting model is combined to achieve zero-shot cross-lingual transfer on target languages, in which the model has not been trained on that particular task. The motivation behind this work is that fine-tuning entire deep learning models is inefficient and can lead to forgetting and interference, degrading performance on previously learned tasks. Here, task sparse fine-tuning is done on languages for which task annotated data exist, while language sparse fine-tuning is performed using mask language modeling. In both cases, fine-tuning real-valued sparse masks are learned based on a variation of the lottery ticket hypothesis, which we will also briefly describe. When pairs of language task masks are composed with the pre-trained model, the number of parameters at inference time and the model architecture are both unaltered, and the resulting models significantly outperform state-of-the-art adapter methods in the zero-shot cross-lingual transfer on multilingual benchmarks. Given the inefficiencies in fine-tuning whole models, adapters are a useful choice to expand the functionality of pre-trained models more efficiently. Adapters are extra intermediate layers that are inserted in a model before fine-tuning. These layers are the only layers trained during fine-tuning, while the parameters of the pre-trained model are frozen. Another useful choice is sparse fine-tuning, where a small subset of model parameters are used. Here, no new layers and thus no additional parameters are added to the model. Instead, a small subset of parameters are trained, while the majority of the pre-trained model parameters are frozen. Now let's talk about adapters in more detail. An adapter layer consists of a down projection followed by an up projection and is inserted after the feed-forward network of each transformer layer. The equation on the bottom left illustrates how this is done at a transformer layer. The hidden state is input to the down projection D, and the output is input to a nonlinear activation function A, whose output is then input to the up projection U, and the result is then summed with the residual connection R. The left figure is an example from MADX, which is the adapter-based baseline used by the authors to evaluate the performance of the lottery ticket sparse fine-tuning method. Language and task adapters are added to each transformer layer. Language adapters are trained via mask language modeling, and task-specific adapters are stacked on top of source language adapters when training on a downstream task, such as named entity recognition. This is shown in solid lines. During zero-shot cross-lingual transfer, source language adapters are replaced with target language adapters. This is shown in dashed lines. Here, we can see the power of adapter modularity, as the number of models we need to train is the number of adapters, which is the sum of the number of tasks plus the number of languages. Without this modular feature, the number of models to train would be the number of tasks multiplied by the number of languages, as the model would need to be fine-tuned for each task language pair. On the right, we see the second fine-tuning approach, sparse fine-tuning, which selects a small set of parameters to fine-tune, while freezing the rest of the parameters. The sparse difference vector, which we call phi, is then added to the pre-trained model parameter vector theta to give the final fine-tuned model. We can see on the right figure and equations how composition is done. We have the red sparse vector, which represents the difference vector after fine-tuning for a language, and the blue sparse vector after fine-tuning for a task. We add both sparse vectors to the model parameter vector theta, which is shown in gray. This allows combining language and task pairs, giving flexibility and efficiency similar to adapter module combinations. The sparse fine-tuning method in this paper is based on a variant of the lottery ticket hypothesis, which is a method for selecting a sparse set of model parameters, typically with the goal of model compression. To do this, the model is fine-tuned on all parameters, and the parameters with the greatest change are selected as the lottery ticket. For model compression, the model is pruned. The lottery ticket parameters are restored to the original values, while the rest are zero masked and frozen. The model is then retrained again only with the sparse set of lottery ticket parameters, given a compressed model that matches or exceeds the performance of its dense counterpart, hence the lottery ticket name. Lottery ticket sparse fine-tuning, which is represented in this paper, does not zero mask parameters, as the goal is not compression. Instead, with adaptation as the goal, the non-lottery ticket parameters are restored and frozen, while lottery ticket parameters are restored and fine-tuned to obtain the difference vector. Next, let's look at the algorithm for lottery ticket fine-tuning for cross-lingual transfer. There are two stages to lottery ticket sparse fine-tuning. Theta 1 and theta 2 are the corresponding parameter vectors, while theta 0 corresponds to the parameters of the pre-trained model. T is the data, L is the loss function, and eta is a hyperparameter for training. K is for choosing the top K parameters after the first fine-tuning stage. In the first stage, we fine-tune the model and learn a binary mask for the top K parameters ranked by magnitude of change from pre-trained values. This is represented by mu. After convergence in the first stage, we have learned the set of lottery ticket parameters. These are the K parameters for which mu is not zero. In the second stage, we start training with the pre-trained parameter values, but only update the parameters for which mu is not zero. The rest of the parameters are frozen. After the second stage of fine-tuning is complete, we obtain the parameter vector phi by subtracting theta 0 from theta 2. This is done separately for every language and for every task. For cross-lingual transfer, we perform lottery ticket sparse fine-tuning in 3 steps. First, on the source language using the pre-trained model and a masked language modeling objective. This gives the phi source or the difference vector for the source language. We add this to the pre-trained model parameters, and this gives a model fine-tuned on the source language. Second, we perform lottery ticket sparse fine-tuning on the task in the source language using the model fine-tuned on the source language in the first step. This gives a difference vector phi task. In the final step, we obtain phi target, or the difference vector for the target language. To do this, we use the pre-trained model with a masked language modeling objective. Finally, we obtain a model fine-tuned on both the task and target language by adding the difference vectors for the task and target language to the pre-trained model's parameter vector. This table summarizes the experimental setup used in the paper. The first column shows the different NLP tasks, while the second and third columns show the source and target datasets. For part of speech tagging and dependency parsing, and most of the languages in named entity recognition, language adaptation is done on Wikipedia corpora. For natural language inference, multiple different datasets are used. The fourth column shows the multilingual transformer models used for the different NLP tasks, and the last column shows the target languages evaluated. Zero-shot cross-lingual transfer is evaluated for 35 target languages across the 4 different NLP tasks. For baselines, they use the MADX as an example of adapter-based models and BitFit as an example for sparse fine-tuning based models. BitFit selects the set of bias parameters as the only parameters to be fine-tuned. They also use a random sparse fine-tuning model where the fine-tuned parameters are selected at random instead of using the lottery ticket approach. Finally, they also evaluate the performance of MADX and lottery ticket sparse fine-tuning when only task fine-tuning is performed. This is done by including only a task adapter or by adding only the task difference vector with no adaptation to the target language. Here we see the results for zero-shot cross-lingual transfer evaluation over 4 tasks when varying the number of tunable parameters measured in the reduction factor for adapters or the equivalent reduction factor for sparse fine-tuning models. The reduction factor is the ratio between a model's hidden size and adapter size, and the equivalent reduction factor for lottery ticket sparse fine-tuning is obtained by matching the number of parameters to the number of parameters of the adapter at a specific reduction factor. For the range between 32 and 1, the number of parameters, or K, varies between 442,000 and 14.2 million parameters. The authors do not observe a large variation in performance with language adaptation based on the number of tunable parameters. So for language adaptation, the reduction factor is set to 2, for a total of 7.6 million trainable parameters. This corresponds to setting K to 7.6 million for language sparse fine-tunings, and results in language sparse fine-tunings with a sparsity of 4.3% for the MBERT model and 2.8% for the XLMR model. The results in the figure are averages over all target languages. We observe the sparse fine-tuning performance consistently increases with more trainable parameters, whereas MADX performance peaks for certain choices of reduction factors. In the top table, we see the results of zero-shot cross-lingual transfer evaluation averaged over all languages for the best adapter reduction factor or equivalent reduction factor, shown in parentheses after each result. Lottery ticket sparse fine-tuning outperforms all baseline models. The performance gains over the random sparse fine-tuning illustrate the benefit of the lottery ticket approach, while the performance gain over the task-only adaptation illustrates the performance of language adaptation. We also observe that BitFit performs much worse than the other methods when both language and task adaptation are performed, possibly due to much higher sparsity when only bias parameters are tuned. In the middle table, we see results for multi-source training experiments on dependency parsing and natural language inference. Here, the training data for all source languages are concatenated. Training data from different source languages are randomly shuffled, and every batch contains examples from one language. The language's corresponding sparse fine-tuning is then applied for this step. The zero-shot cross-lingual results here are also averaged over all target languages and show that multi-source training significantly outperforms single-source training for the two dependency parsing metrics labeled and unlabeled association scores, while providing a smaller improvement in natural language inference accuracy. The final table shows results of zero-shot cross-lingual transfer evaluation for question and answering on 5 target languages not present in the training data. For each language and model, the F1 and exact match scores are given. The first 2 rows show results for full fine-tuning for the base and large architectures, while the last model is obtained using lottery ticket sparse fine-tuning performed using multi-source training with additional languages beyond English. We see that lottery ticket sparse fine-tuning with multi-source training of XLMR base outperforms single-source full fine-tuning for XLMR large significantly, even though it's a larger model. It outperforms XLMR base single-source full fine-tuning by an even larger margin. This demonstrates the benefit of multilingual source training, given that the non-English datasets used are smaller than the English dataset size by an order of magnitude. This concludes our discussion of the paper. Thank you for watching.